screen. You can see the slides okay? Awesome. Yeah, so feel free to interrupt whenever you have any questions. So I'm Ishen, and I'll be talking about some of the work that's being done in Alessandro's lab, which is the HIRO lab and stands for Human Interaction Robotics Group. And I'll mostly cover one of my previous projects, and then I'll briefly talk about how you might be able to get involved. So, the HIRO lab, we work on robots that work with humans and around people. And we work in this field called human robot interaction, where we try to bring robots into environments with humans, where we try to augment the physical capabilities of humans and also the social aspects. And we've seen a lot of robots being deployed in factories, in cages, where they perform dangerous tasks alone. But instead of this paradigm, we want to bring robots into human environments where they can help people. So we see applications in also in logistics, manufacturing, in healthcare, and service and home robotics. And this is the lab. It's somewhat of an outdated picture, but we have three different strands of research, learning modeling and robotics that look at motion planning, deep learning models for generating robot actions. And recently we've been looking a lot at using diffusion models. We have in the middle physical HRI, where we design sensors that we can place on robots to give robots a better understanding of its environment, um, so that it can better make plans and avoid collisions. And then we have algorithmic and social HRI, where we design algorithms for um, interacting with humans and predicting human behavior, um, and using those predictions to make plans. So, yeah, these three different research strands. I will mostly talk about a project that I think sits in the algorithmic and social HRI. So this was a paper presented this year at the HRI conference, and it's titled Workspace Optimization Techniques to Improve Prediction of Human Motion During Human-Robot Collaboration. So I will yeah, get started on this. So to have an effective human-robot team, we need to be able to predict what our teammates are going to do. So for this collaborative assembly, the robot is trying to predict what the human is working on, and given that, it will bring the human the correct part that the human needs. So it has to be able to accurately predict the human's actions and what tasks they're working on. And if we have a robot in the hallway, both the human and the robot would prefer an agent that is predictable so that we don't have behavior that's unexpected and may cause to collisions. And here we have a collaborative setting where they're carrying some big object. And as humans, when we do this task, we have implicit understanding of, how to move the object uh, based on, if the human faces their back to the door, they're probably exiting the door that way. So there's some implicit understanding that the robot would require to perform this task successfully. So we need to have, in all these scenarios, we need to have, predictable teammates to have these effective collaborations. And when robots become unpredictable, we may have undesirable interactions, such as this one, when the human got surprised of that the robot got so close to it, right? And this unpredictability also makes it difficult for the robot to plan. So let's say we have an autonomous car, and there's a human here that looks like it's trying to cross the street. So there's a crosswalk here. And if the robot has high confidence of the human's actions, so this uncertainty of humans' actions is very small, it thinks the human's probably going to go through the crosswalk. This can lead to, potentially dangerous interactions if the human doesn't follow what the robot predicts. But if the robot or the autonomous car has high uncertainty of the human's actions, so it thinks it can jaywalk, it can go to the crosswalk, it might be overly cautious and go kind of slowly even when it doesn't need to be. So, what are some of the work? What have people done to try to enable predictability? So this is one of the prior work published at HRI quite a while ago now on intent expressive robot motions. So it formalized the idea of predictability and legibility. So if we focus on this on the left, given a goal, um, predictability measures how well I can predict the trajectory that it takes to the goal. So here in mathematical terms, they define predictability of a trajectory as the exponent of the negative of some cost function. So this cost function we can assume to be just the Euclidean distance for now. So this is saying that the more efficient a path is in terms of distance, the more predictable it is, right? Which makes sense. If I know that the robot is gonna pick up this green circle, the predictable path is the straight line path to it. Now for legibility, it's the other way around. So given some trajectory, the the legibility of a trajectory is how well you can predict which goal that they're going towards. So here there are two goals. There's the red and the green. Um, by taking this kind of a roundabout path, uh, it is more legible because now I can quickly determine that, from this second step, that the robot is going towards the green object instead of the red. But if we have a predictable path, it is less legible because now it's harder to tell which one it's going to pick up until later on in the trajectory. So through this framework, they were able to show that robots that perform legible motion has more fluent collaborations, and it improves the overall task efficiency for collaborative tasks. And participants also have better perception of the robot with legible motion. So if we look at these two types of motions, right, we see an inherent trade-off between legibility and efficiency. The more legible a motion is, it could be less efficient for the robot to do the task. So in this project, we came up with this research question: can we achieve the benefits of legible robot motion by designing the environment, by making the environment more legible? And this came from, this insight that how legible an agent's motion is depends on the environment. So in this, kind of a contrived example, but we have an agent trying to go to the onions or the tomatoes. And when it's going through this long hallway, it's impossible to tell what they're going to pick up. But in a different environment, we can immediately tell which way the agent is going. So the main contribution of this work was introducing this algorithmic approach for to enable a robot to optimize its workspace by rearranging the objects, the physical objects. And we also used augmented reality to project these virtual obstacles that serve as barriers so that uh, the human cannot cross through these barriers. And we're able to show that this improves human goal prediction um, by reducing the uncertainty in the human motion. So some of the challenges that we faced, we want to find, the goal is to find an environment that is legible. And the space of possible environments is very big. It's a high dimensional search space. Even in this, grid world environment, we have different ingredients, the placement of, the fish, onion, tomatoes, cabbage, um, whether to place this virtual obstacle or not in this open space. So there are exponentially many number of possible environments. And evaluating an environment is also expensive. So once we sample an environment layout, we have to calculate how legible this environment is, which I'll go into later, but it's expensive um, to come up with that legibility score. And then lastly, we can't really run gradient descent on this. We cannot assume that we have the function, delta legibility over delta E. It's not differentiable over the environment parameters. So it's hard to guide our search to minimize or to maximize legibility. So we used a evolutionary algorithm called map elites. And the idea is that if you have some high dimensional space where you want to run optimization, the we can use the designers, so the user of this algorithm, domain knowledge to design some features where they think is important. So once you pick some set of features, they're showing two, feature one and feature two. I can store populations of um, I guess in this case, I'm generating environments. So these are different environments, and I store the best environment for that, for every possible combinations in this feature space. So looking at this picture on the right, here we also have, they call it behavioral dimension one and two, but they're the feature space. So let's say, um, one of the features of my environment is distance to the onion from some start location. Maybe I can have distance to tomatoes for my other feature. And then each of these cells would store the best environment found given with those specific features. And then I would perform um, this algorithm would sample from my current map, perform some random variations to update the environments, and then I would reevaluate it. So this new environment would probably sit somewhere else in the feature space, and I would store that environment in that new cell if it is the best one found for that cell um, so far. So this is a good method for searching through a high dimensional complex search space and that no gradients are required. It's a evolutionary process that maintains this population of what they call elites. So I'll go more into detail uh, this as well. So this is for this grid world domain that we have based on over the overcooked game, where you want to collect these different ingredients, place them in the pot, and then deliver the soup. So the features that we chose were the number of obstacles that are in the center and some the ordering of these ingredient placements. And so each of these cells are the performance of the environment that was found through the algorithm. So this algorithm has two stages: initialization, where we sample random environments, evaluate it, and then place it in the map. And then we sample from the map, add perturbations to improve the solutions that we have that are in the map. So here's just kind of illustrating that when we sample an environment from the map, we add perturbations by adding obstacles, removing obstacles, moving the ingredient locations, and then we store all of these back into the map. So now I'll talk about how do I come up with how legible the environment is. So here we simulate, these are the different goals that that I have in the environment. I have onions, cabbages, dish, fish, and tomatoes. And so I pick a goal, a ground truth goal, and I simulate a partial trajectory. And I compute this goal probability based on this equation. I think I haven't really talked about this, but um, this is how efficient the probability of a goal given your partial trajectory is proportional to how efficient this goal is given your current trajectory. That's the main idea here. So for the legibility score, I simulate this partial trajectory, I compute the goal probability, and if the argmax of this goal probability distribution, what I'm predicting to be the correct goal, is incorrect, I penalize the legibility score by the trajectory length times some constant c. And if it is correct, the score is the difference between the highest and the second highest probabilities. So this just kind of encourages um, more confident predictions. And then that was the legibility score for a single ground truth goal, right? Now I have a task, which is defined by a task graph. So the task might be to collect two onions, one tomato, place them in the pot, and then deliver it with the dish. So I consider all possible permutations of doing this task, and then I sum up this nth legibility for each of the ground truth goals in that task. So this forms the final legibility score for a single environment. Are there any questions so far? That was gone through quite a lot. Yeah, I think I see a raised hand. Go ahead.
Hi, thank you for so far explanation. I wanted to know, like, yes, you have defined the like what would the problem statement and how you are going to approach it. But my
Yeah,
question is like, what have you tried mimicking the human behavior in it?
mimicking the
Have you-
human behavior.
Yeah,
Yeah, so
yeah,
uh, you mean when I simulate the human actions?
yes.
Yeah, so that part is not included in the talk, but let me go to here. The cost function that you see here, we actually use IR, inverse reinforcement learning, to learn this cost function um, from data that we collect from we use Mturk to collect human gameplay data, and then we uh, update this cost function. So this can be you can use heuristic, such as just the shortest distance to the goal, but then we were able to show that if you use IRL, it does provide better prediction for some of the tasks, for some of the going to some of the goals.
Mm-hmm. Yes,
Yeah,
that only yes, we can I guess you are moving with the statistical decision than the mimicking the human behavior. But
yeah,
uh, yeah, I guess that's tells me. Yeah, thank you.
yeah. That's one of the ways we evaluated it. But when generating this environment, we use the heuristic, the shortest distance. Yeah, that's a good question because in the yeah, that's why in this paper they left the cost function C arbitrary, I guess, because you can learn this from data, you can use domain knowledge, or yeah, you can model it um, in different ways.
Yeah, thank you.
Yeah. So I'll yeah, kind of quickly talk through the experiments that we ran. Um, for this grid world environment, we have uh, random, where we just randomly sampled 1,000 different environments, sorted them by the legibility score, and then we picked the median one. We had an environment optimized for how efficient it is to accomplish the task. So we had a constraint that these ingredients had to be, one cell away from each other. Otherwise, the trajectories would be too short, and we know that if things are crowded around, it's hard for two agents to collaborate because they'll kind of collide all the time. We had our approach legible, and then we had one condition where we combined both the legible and efficient objectives. So here we're plotting on the x-axis the percent of trajectory observed and the accuracy of predicting the correct goal. Um, and we're able to see in most cases the legible condition is has higher accuracy compared to these baselines. So for the other experiment, we had a tabletop collaboration domain where the goal is for the human and the robot to move these cubes in some desired configuration on this side of the table. So it represents like a, sorting task or where they have to um, share the same workspace. And so I'll just play this again. So here the robot is in real time predicting the human's goal, and then once it's confident enough, it would go and pick up a different cube to advance the task. And on the right side, we see the human's view from the HoloLens. So you can see the um, virtual obstacles being projected. And here we have a baseline condition where the cubes are initially sorted by just their color and their shape. We have our approach, which we call both optimized, that use the algorithm described to organize the positions of the cubes. And then I didn't talk about the virtual obstacles too much, but they were also um, part of the process of when you add perturbations to the environment. So this was kind of interesting because it makes sense to add these as barriers. It seems like it's dividing the cubes into, these different sections. But this was all algorithmically generated, so it can be in any orientation. We tried different sizes of these barriers, and pretty amazingly, it did come up with something that felt like it makes sense. And then we have the two ablation conditions, where here you can only place virtual obstacles, and then here you can only modify the positions of the cubes. So this is the part where we train a model to predict a human's goal. So we used an approach called the time series multivariate Gaussian. And so here we first collect, human hand trajectory data. And this is a real sense camera mounted at the top of the workspace. And we use media pipes, the hand tracking system, to generate when it detects the human's hand, we get the mean, the middle of the hand, the XY position, and then we store that as trajectories. So we collect, let's say n trajectories for each of the goals. And since these trajectories have different lengths, we have to align them to see what are the points that are supposed that look the most similar. So we use dynamic time warping so that they would have the same number of time steps for all the trajectories. And then we fit a Gaussian for every time step of the trajectories for each of the goals. And during inference time, when we get a partial human trajectory, we look at the probability of predicting a goal is the likelihood of that partial trajectory coming from the learned Gaussians. So then we compare this for each of the goals, and the one with the highest probability is the predicted goal. So here we are plotting the same point of view from the top of the workspace. We're plotting the learned Gaussians along with, the mean and the covariance for each of the conditions. And we can see that, with the workspace optimized condition, we have a lot less a lot less variance in the human's motion, which makes it easier for the ML model to predict the goal. So here I will show an example of the baseline condition where um, we stop this prediction, right before the human picks up the cube, because by the time you pick up the cube, you know the goal 100% of the time. So right before the human picks up the cube, it's difficult to identify using our goal prediction algorithm which cube the human was picking up. And through our approach, we can quickly identify the correct goal, which makes it easier for the robot to collaborate with the human. So in summary, we show that human motion prediction is dependent on the environment in which they're interacting in, and that we can utilize the workspace to reduce the uncertainty of the agent's motions in the space and improve goal predictions to make collaborations easier. So here, briefly talk about what are some of the best ways to get involved. There are quite a few labs in the computer science department for robotics. And there are, you can find the labs websites with the most recent publications and the current students and what they're working on. So it's good to first start there to figure out um, what are some of the most recent works, and and then you can reach out to the PhD students who worked on those papers. Um, Mention, what are you interested in? Maybe if some of your background fits with particular parts of the work, that would be really helpful. But prior experience is not always required. If it's something that you're really interested in, feel free to reach out to the PhD students and the faculty. And generally, we do look for um, people who can spend a decent amount of time either, uh, you know, during the semester or the summer, because these projects take a really long time. And usually it takes more than a year for a paper to be published. So it's good to get involved on projects early. And that's all I have. Happy to take any questions about the lab, about what other, projects are happening. Yeah. Yeah, I see a hand raised. Susha?
Yes. My question again go back to the planning with
Yeah.
too little or too much uncertainty. So,
Yeah.
question is like, what were the outcome of this study? Like, was it too much uncertain, or was it little certain?
We mainly show that we can modify the environment to change how uncertain the human motion is. By modifying the placement of objects, um, that we can improve
Yeah.
the the human
So,
goal prediction. Yeah.
my question was like little bit of like how robot behave when when it comes to like doing the actual experimentation. Like, was it too
Yeah.
uncertain or something like that?
Was the robots
What's
uh
uncertain about it, or was it optimal thing that you have think or thought, and how did you check it?
yeah, you're talking about the robots planning. What what's the
My question is
uncertainty
like,
over?
yeah. So my question was like, yes, robot did the sorting as per the requirement. So how did
Yeah.
you check about it, and what were your conclusions based on it? That was it certain behavior? Was it uncertain behavior?
Yeah, so in this experiment, right, the robot always predicts the human motion first before acting. So um it would so I you can use different algorithms, but I had a threshold for how certain its prediction of the human goal is before it can start acting. And so the robot would kind of wait and then look at the human's actions. And then once it's certain that the human's going to pick up a certain cube, then it looks at what cube can I pick up next to advance the task.
Okay.
Is that what you were asking?
Yeah, so it means that it is not directly mimicking the or it's just predicting what will be the my next move is.
Yeah, based on what it thinks the human is doing.
Yes. Yes.
Yeah, yeah,
Thank you.
yeah. Luna?
Yeah, so I know that the HIRO lab has previously done a very small amount of research into NLP for HRI. Do you know if there's interest in the lab of doing more work in that area, or would that be a better question for an email to the folks who were involved in that specifically?
Yeah, that's a good question. There's definitely interest in now that we have access to LLMs. There's a lot more people looking into that. Stefan, you'll be able to find his profile email on the lab website. He worked a lot with natural language and robotics. And his most recent paper, it's under submission though, but it is using NLP to do preference learning.
Oh,
And yeah, I think we're also getting, more resources on we're now able to fine tune um maybe some of the smaller VLMs, and
mhm.
uh we're looking at we're looking at octo models. It's a diffusion based robot policy model. I think and it takes in language prompts. So yeah, there's definitely a lot of work. And um yeah, if you're interested, uh email out to yeah, see if there's something we can work on.
Okay, fantastic. Will do. Thank you.
Thank you. Okay. Anand is next.
Yeah, thank you. So my question is like, I wanted to know how adaptable the current sensor units in the system are to like other sensing modalities such as like EMG or like computer vision, like for enhanced detection of human movements or intentions and like managing the human unpredictability.
How adaptable? Yeah, so at least for this work, the I guess I can talk about this. At least this method, it doesn't matter. It can take in many different modalities. It just needs using all those different modalities, you'll try to fit Gaussians on these different inputs, and then use those values to predict, uh, I guess, human behavior in in different contexts. I haven't done that myself. I've only mostly used cameras and try to get, human skeletons from like the hand skeletons. There are models that are available to do that, and then using that as input to predict the human goal or activity that they're doing. Yeah,
Uh,
so I've only worked with um, image data, but I think it can extend to different modalities, and they should help. Um,
Makes sense.
yeah, there's a recent paper in the lab on using eye gaze, which I think is also interesting.
Uh, yes, it definitely is just um, like human behavior can be predicted by accessing multiple sections of sensory output, and like if we can somehow use like multiple of those, I think that should make the behavior more predictable in the long run.
Yeah, yeah, there's a lot of work on multimodal, using deep learning models, and then you have these different modalities of human data. How do you like combine them to make your
Mhm.
model predictions better?
Also, I wanted to ask like what the potential applications of these like sensory or robots are in assistive robotics for like people with motor disorders, or like how the team see this evolving. Who would be a good person to reach out to like have a conversation on this?
Yeah, so um, I'm also advised by Bradley Hayes, and uh, one of the PhD students is currently working on uh, assisting visually impaired people with grocery shopping. Oh,
Hmm.
Shivendra. Yeah, if you check out the HIRO lab or Bradley Hayes CU Boulder, you should be able to find the lab website.
You said
Um,
Bradley Hayes.
yes.
Okay, thank you. Thank you so much.
Yeah. It's cool that you brought that up as well because I'm trying to extend this current work to um, assisted feeding because
Mm-hmm.
for patients with motor impairments, the wheelchairs so the wheelchairs are equipped with joysticks, so we have to try to map joystick input to a robotic arm to actions for the robot end effector.
Yeah,
And yeah, we're trying to work on some of that as well for
that's really valid work.
yeah, thanks for the question.
Of course.
Yannick?
Hi, hi, Yashan. So my question was regarding the eye gaze study that you just referred for this. Someone worked on eye gaze modality. So could you tell us like a little bit more on who did that work? What was the work?
Yeah, it was also Stefan. It was using eye gaze. They also used the overcooked domain with the collaborative cooking game, and they were trying to see if including eye gaze data, can you better predict um, their goal or their strategy? So the robotic agent, the AI agent that's trying to collaborate with the human in the game, and um, better, utilize a policy
Oh,
because you
okay.
can,
Yeah.
yeah, the AI agent would have to use different policies or strategies for collaborating with humans with different strategies. Just kind of why the game is kind of a cool test bed um, for collaborative AI.
Sounds great. Okay, thank you.
Yeah.
Okay, one more last question that I wanted to know. Do you
Yeah.
know if professors are looking for PhD students in Hero or Cairo?
Um, ooh, that's a hard question. Um, research experience in the lab is definitely helpful. I guess working in a lab, your goal would be to gain experience on what research is like, and then, ideally publish a paper as a co-author, and then, yeah, I don't really know. Might be a better question for the professors, but I think having experiences in the lab would be would be helpful.
Thank you. Thank you for that as well.
All right. Anyone with any last questions? All right, well, we appreciate everyone's time. And that was a great presentation. I recorded it, and it's going to be posted online if anybody would like to review it.